now this presentation is going to be in English, but I'm going to make it in Turkish. But I don't know the Turkish version of some of the terms, so I'm going to say them in English. Apologize me. I'm coming from Delft, the oldest technical university in Netherlands. I'm in the aviation faculty. And there are almost 2,400 or 600 students there, and I'm in the material and construction department of this faculty. There are 4 groups at the moment. And I have to say that as we're in very close contact with the aviation sector, and what we are starting from is the molecular level. So we are working on different levels. I am in aerospace manufacturing department. We are mainly responsible for manufacturing. We have 2 more groups, computational mechanics and structure, and the composite group.
Var ve orada da birkaç yıl önce kuruldu. Daha ziyade otomasyon.
We have a sister organization where there is an automation related work. And apart from low TRL, they're trying to fill the gap between industry and the academy. We have a very big laboratory there, as you can imagine. And based on my research, I can easily say that the composite materials, I'm sure you're all aware of this, start with fibers and extends to and in the lowest scale, we have ultra thin plastic tapes, and again, apart from the academic work, we have industrial manufacturing machine which has been recently bought, mainly focusing on natural fibers or those fibers which cannot be stretched along. And it is about the integration of these fibers. And again, as we know that one fiber may not be working in the same system like the other one, we have different types of approaches. We have physical modeling in almost every type of our work approaches. And we are adding the artificial intelligence to each and every project. And again, it is possible to predict these, make a prediction in seconds. And as we're based in Netherlands, I don't know how it would be right to say that it is the motherland of the thermoplastic, but on the other hand, on the sustainability side, there is this pronto mobilization, and it goes on based on it. And again, we have tape manufacturing, and even though the scales may differ from one to another, and the processes like RTM and their optimization, we have academic and industrial works on this. And on a larger scale, this is something that we work very closely with, and it's a big consortium in the Netherlands, ultrasonic source.
listeye henüz koymadım.
Well, we have so many works about the recycled materials as well. And again, now, I am going to talk about what we are mainly working on. And I'm going to tackle 3 topics much more detailed than the others. But if you have any questions, please do not hesitate to ask whatever you would like to ask, okay? Now, as I said, ultra thin or thermoplastic tapes are the main matter of interest to us. And to produce a very thin tape, like 24, 6 or 3K, comes from dispersing the carbon fiber, first of all. And of course, you have so many advantages with respect to this. And the thinner the better the thickness is, the mechanical structure, the mechanical qualifications. This is, for instance, T18 fiber. Whenever the thickness goes down, it becomes thinner, your mechanical qualifications get closer to the mechanical fiber qualifications. This is where we start working on. And this is the automation-related process, as this is very well, and we would like to make it up to the limit. And again, we are working together with the pioneers in the industry in Netherlands, and the purpose there is these ultra-thin thermoplastic tapes to be used for liquid hydrogen tanks. And as I said again, we made lots of investments, and again, we're not, of course, going to start working on it immediately by buying the machine. We are working on the academic side of it at the moment. And we have the spreading bar. Spreading means to spread the fibers all around. So these spreading bars. Now, we have a small arrangement in our laboratory already, and we have spreading bars. And again, we have the tension sensors that are sensitive to stretching. And for about a year now, this spreading process, in order to understand the reasons behind this spreading process, we're carrying out many activities, and there are so many parameters. Well, of course, you always want to stretch it as much as possible. And again, the roughness is also very important. We're working on these. And this spreading process has been modeled like this, on layer belt. On layer band. Well, let me ask you a question then. In terms of orienting the fibers, we have some problems. It's not possible to hear the speaker at the moment. Efendim, konuşmacı şu an duyulamıyor. The cross interlinks can be a reason for your work, and these are all valuable to us. The better you spread, the better for us. Then we are going to be able to carry the weight as much as we can. The rowings, for instance, the tapes, the band production process, or as you're feeding many rowings all at the same time, you're able to see that the flatness of that product comes around. And again, it is very important to understand the reasons behind it. That's why we're working on this. And this conveyor bands. And there were some models that were used to model these conveyor bands, to model this process. But our work so far has shown that the stretching power, the diameters, the radius of the spreading bars, and their surface and roughness are some of the various parameters as far as we can say. And of course, you can just question the modeling side of it. Why you need modeling? For some of the occasions, you may need hybrid composites. When it is a hybrid material, then you may not know how to go on with the process. And then we come up with the modeling. And the next topic that I'm going to be talking is going to be about the artificial intelligence. As I say, I'm very active on the thermoplastic. And the characterization and modeling was my PhD thesis. So we're working with many different types of processes, but we also have RTM. We are trying to develop an RTM variant, for instance. And in terms of the infusion, following up of the flow, and it is very important to follow up this model. And again, in RTM-like processes, based on the flow process, there may be some vacuums, and you may again use a model to predict where it is going to occur. And on the other hand, we have different types of models. We can understand these through the physical models to an extent, but then we have some trends, and these models are not able to catch up with them. Therefore, we're using the data we have in hand, and we're using the methods there in order to catch up the models, and we are just trying to figure out where that trend is going to be. And the most significant example comes from a publication we recently did. I'm not going to go into the details, but there is a neural network conventional, an artificial intelligence method. By using this, we've done something. Normally, in order to predict how this is going to be impacted, you have to make some predictions. Based on my own experience, I can only make some estimations, and it is never longer than a couple of hours, I have to say. And you can just disseminate different types of structures. And when you make a prediction based on the artificial intelligence, then, as I say, again, you have an acoustic camera, and again, here, it is going to give you some information about how that comes out, and when you have to stop it, and how much strength you're going to be applying. And on top of this, again, Airborne, a company very well known in Netherlands, is pioneering this RTM, automatic RPM process. Is going to help us to come up with a closed box process. And again, I don't want to go into the details. Physical based predictors are as successful as this one we have. And what we see here is, well, there are very simple models in literature. And again, for this high performing performance, we see that there is a diversion. And again, in terms of the prediction quality, it is possible to make the estimations in the accurate manner. And in the last trial, the last study, we were in Switzerland, and again, as I said, the interest into thermoplasty today is increasing day by day. And again, there are so many advantages in terms of recyclability, but we haven't yet arrived to the point we are trying to. And again, a large part of the energy need comes from fiber production. Autoclave or RTM-like processes are either requiring a big pressurized furnace or a mold, and we're trying to figure out how we could reduce it. I'm going to show you two videos, if you allow me. On one of them, you're going to see the scenario with the resin. And again, you're going to see the UV light as well. And you're going to see a hot metal there. Well, this is never a very simple process, as you can imagine, because on one side, in order to see curatization, you have to see the disseminating energy activating, and a part of it goes to the fiber, and the process control is possible. And we're working on this at the moment. As far as we can see at the moment, there's a 5 centimeter progress per minute, and it is possible to see this. And in terms of viscosities, we usually see this again and again based on the first calculations. We need less energy. Now, as for the final thing, in Delft, in the manufacturing group, I'd like to share what we do there. And as I said right at the beginning, we start from the smallest scale and reach up to the highest one. And of course, our contact with the industrial partners is increasing in this respect. And the modeling is also a part of it. And we're using the artificial intelligence tools as much as we can in this respect. And as for the final thing, I would like to thank the researchers who have contributed to what we're doing at the moment. Thank you very much.